Chapter 6, Section 5, Complex Rational Expressions. So we're going to basically look at fractions of fractions. That's what they mean by complex. And we're going to use division to simplify, and another method is multiplying by an LCD and using that multiplicational, of the identity of 1 in a special way, a strategic way again. But first let's look at this division to simplify. A complex rational expression is a rational expression that has one or more rational expressions within the numerator or denominator. Here are some examples. So if I have, in this case here, I have 1 plus 2 over x in the numerator and 3 in the denominator. So on, here's a fraction over a fraction. Here's an addition of a fraction over a subtraction of fractions. So really it's fractions of fractions, and that makes them complex. So we're going to really we're going to follow all the rules we deal with fractions, and there's nothing really new. This is really strategic applications and trying to say, well, what are good ways to deal with these types of rational expressions. So the first method they're going to show us, or basically this is a strategy, a problem-solving strategy again. Our first method is simplifying this complex rational expression. Involves rewriting the expression as a quotient of two rational expressions. In other words, we're going to go back to this like this one and say 1 plus 2 over x divided by 3. In other words, we're going to take one of these fraction bars, the main fraction bar, and treat it like a division. And to simplify these, we're going to add or subtract as needed to get a single rational expression in the numerator. Add or subtract as needed to get a single rational expression in the denominator. And then divide the denominator by that invert, basically create a division, and then convert to multiplication, and then finish that by simplifying. So let's look at some examples here. And this is really some good text in here to read and review too. It says the key here is to express the complex rational expression as one rational expression divided by another. So in this case, that's already here. I have a fraction on top, x over x minus 3. And here's a fraction here of 4 over 5x minus 15. And I notice right away that we can factor some stuff, but let's just stick to the solution first. They say, well, I can take this fraction and say this big division bar here is really division. So they rewrite this as division. So one fraction divided by this other fraction, the denominator. Numerator divided by denominator. And when we convert to multiplication by inverting or taking the reciprocal of the divisor, which in this case is 4 over 5x minus 15, and we created a multiplication. Prime factor, we look for common factors. In this case we have x minus 3, so I end up with x times 5 over 1 times 4, which is 5x over 4. So that's what we do. Now in this case, the next step would be we want one fraction over one fraction. So this, to stay in this method, in this strategy, is we're going to take the numerator, in this example a, and this 5 over 2a plus 1 over a, and actually perform that addition. We can do that, and so you just treat this as its own thing here. And let's look at the numerator here. Well, the common denominator between 2a and a is 2a. So to change this 1 to be 1 over a to be something over 2a is you multiply by 2 over 2. And so we get the addition done here, right here. I'm kind of skipping. They're doing the same thing with the denominator, showing a lot more work. But let's focus here on the numerator first. So we end up with 5a over 2a plus 2 over 2a. So I can add these because they have the same denominator. I get 7 over 2a, which is in simplest form. Well, the denominator in this case, which is 1 over 4a minus 5 6, same process here. How do I get a common denominator here? I just treat the denominator right here, so we're focused in on this again. So I rewrite these fractions so they have a common denominator of 12a. So now I end up with 3 over 12a minus 10a over 12a, which ends up to be 3 minus 10a all over 12a, doing this subtraction. Okay, so now then I would check, make sure anytime you add or subtract fractions, you should check to make sure you're in simplest form. Well, there's no common factors between these two terms, and so I don't have anything to simplify. So here I have a fraction over another fraction. So then I do the division. Treat that as division, convert to multiplication, and by inverting the divisor or taking the reciprocal, and then I look for common factors as I'm multiplying. Notice they don't go 7 times 12a and say that that is 84a. They leave it prime factors as you're going because, hey, I might have some common things here that will do that. In other words, they prime factor 12a to be 2a times 6, okay, because I might have these common primes, okay, which is removing the factor equal to 1. So I end up with this 42 over 3 minus 10a. And that's in simplest form if we didn't miss any common prime factors. Now in this case on B we have a subtraction of fractions over just a multiplication here. So perform this subtraction so they get a common denominator of xy. So you take x squared times x over x, y times x is xy. You take 5 over x times y over y, you get 5y over xy. That's where they got this part. Then do the subtraction, so I can rewrite this since I have a common denominator. I can write this as x cubed minus 5y all over this. Now, why they're using this example here too, because we're so used to this having a fraction here in the divisor, because really now I have a fraction divided by xz. Well, I can write that as a fraction. It's really xz over 1. So when I take the reciprocal of xz, usually people will see this when I put this in a fractional notation. Well, it's 1 over xz. So then I have this multiplication. I look for any common prime factors. It doesn't look like there are anything here in the multiplication, so I multiply. I get x cubed minus 5y over x squared yz. And I'll stop here. I'll make another video on multiplying by the LCD.